Welcome to our second lecture on continuous random variables. This one's going to focus primarily on these sampling distributions, although we will touch on a few that we've missed, and hopefully after this lecture we will be wrapped up and have a good set of continuous random variables to go into our next topic, which is going to be sampling and data analysis. As always, let's begin by recapping what we learned in the last lecture. Let's recall that we introduced the concept of the continuous random variable, which differs from a discrete random variable for a few reasons. Primarily because it exists on an ungapped or infinite space, and as a consequence of that, the probability of any one of these values for the continuous random variable is zero, although of course that doesn't mean it cannot occur. It just means that the probability of a single event out of an infinite amount is zero. We also talked about how we can move between the two, how we can partition a continuous random variable into pieces, name the pieces so they correspond to a discrete value, and then our continuous random variable will function like a discrete random variable. And additionally, we talked about how the limit distribution of some of the discrete random variables is continuous. And our primary example was how we introduced the central limit theorem, right? We talked about throwing an infinite amount of six-sided dice and then taking the mean, which of course would give us an average of 3.5, but instead of being uniformly distributed like a single toss of a die, it would have a normal distribution. So while we did not discuss this in the last lecture, it was part of our discussion section and it is part of the homework. We do have another pair of discrete and continuous random variables. We have the geometric random variable and its continuous analog, which is the exponential random variable. Recall that the geometric random variable describes the number of failures until a success, and we could imagine that each failure can be thought of as a unit of time, right? You could be doing some task, and each minute you could either fail or succeed. And of course, once you succeed, you'll stop. And the geometric random variable can describe how many minutes until you succeeded. Of course, minutes are usually thought of as a continuous quantity. So what you can do, right, is you can turn the geometric distribution where there's an infinite space for failures just becomes the exponential distribution. And that will better model a waiting time because you have a continuous quantity. It would be a proper recap if we didn't talk about two of the most important concepts that we've learned all year. Those are, of course, the law of large numbers and the central limit theorem. The law of large numbers talks about how as we increase our sample size, the variance in our estimation of the mean goes to zero. One way to think of that is that that's the destination. And of course, we have the central limit theorem, which talks about the journey, which says, yes, as the sample size increases, the variance around the estimation shrinks, but what's more important is the shape of the distribution is normal or Gaussian distributed. The single idea of convergence to the normal under addition actually kind of spawns two different ways of thinking about the usefulness of the normal random variable. So the first idea is, well, many things in nature, for example, the height of humans, we can think of that as a combination of the height of their parents and the height of their grandparents and maybe their diet and many factors, seem to come from an additive process, and so therefore are expected to be normally distributed. Additionally, it says the normal distribution is very useful because if we aren't sure if things don't come from an additive process, like for example, the tossing of a single die, well, that's okay. If we're able to repeatedly sample, we can just look at the distribution function of the random variable that describes the tossing of, say, 10 dice, and that will be normal. So it tells us that we have basically two options. Assume it's normal based on some either sampling criteria or something that we know about the origin of the process that describes the random variable, or make it normal, if possible, by adding multiple copies of the random variable and taking, for example, a mean or some other weighted sum. One thing that's important to note is that there are many processes in nature that are additive, but there are also something called multiplicative processes. And an example of that might be income. It might be the size of a river or the height of a mountain or the population of a city. Anything which grows according to the proportion of what's already there. So these processes actually won't look normal because they're not growing through addition, they're growing through multiplication. Luckily, we have a little trick for this case, right? So if a random variable is generated from a multiplicative process, then what we can do instead of analyzing the random variable, we can analyze the logarithm of the random variable. And then what we'll notice is that the logarithm will be distributed normally. And that's of course because in log space, multiplication is addition. For example, what we can do is we can use our multiple die approximation for the normal, and then we can sample from there and we can take the logarithm of the result and use this as our random variable. And you can see that this has a typical log normal shape. And in the bottom in the orange box, what we try to see how we can generate this process with a genuine multiplicative process. So here what we're doing is we're just allowing the random variable to start with some initial value, which is 1, and then we're just going to repeatedly throw a single die, and we're going to multiply by 1.1 or 1.2 up to 1.6, depending on the face of the die that's pointed up. And we're going to continually do that for so many tosses of our die, and we see that this does not converge to a normal distribution. The reason why it doesn't grow normally is because the normal distribution is the outcome of adding multiple things. And here, rather than adding, we're growing. Naturally, the distribution we see, well, it's not normal, the logarithm is, and we're okay with that. So that's a good solution. So with that in mind, we can now start to analyze data, make observations, and make statistical inferences using the log normal and the normal distribution, right? Fortunately, the answer is not yet, and that's what the rest of this lecture will be about. So why can't you go wild making inferences using the normal approximation? Well, to see why that's problematic, let's think back to the first day of class when we introduced this really important concept called bias. We talked about how the estimation of the variance using the sample mean gave us a biased result. We talked about, of course, how the mean was unbiased because, while of course the estimation of the mean is not guaranteed to provide the actual mean or the expectation of the random variable that's underlying the sample, the probability of being too high in the estimate of the mean or too low is equal. So variance, if we use the uncorrected estimator for sample variance, which of course is just xi minus x bar squared, the sum of this divided by n, we persistently estimate the standard deviation or the variance to be below its true value. And of course that's because the sample mean is always the value that minimizes this sum. We talked about our solution, which we didn't love, right? Which was to use the Bessel correction, which was just to, instead of dividing by n, to divide by n minus 1. And we noted that while that reduces the bias, it does increase the mean squared error. So we now have an estimator that's no longer biased for sample variance, but the mean squared error is higher. So while we can correct the bias, we of course pay a price for doing that, and that also is going to make us pay a price when we try to use these estimated parameters and plug them into the normal distribution. What we're going to do is we can just generate samples from a normal distribution. We can standardize the mean, and we can look at how many standard deviations our sample mean is away from our true mean and make a prediction as to the p-value for that observation. So at a p-value in 1 in 1,000, we're seeing more than twice as many samples as we would expect, which is going to increase the false positives by a great deal. So to get a handle of what's going on, you can look at the blue and red curve. The blue curve represents the distance from the true mean that we observe in our sample after we standardize it using the parameters of the random variable used to generate the data. And the red curve is the same thing, only instead of using the variance parameter, use the sample variance to calculate the standard deviation and standardize our random variable. And what we're seeing is when the sample size is small, the red curve looks very different than the blue curve. So the red curve is sort of all over the place. And as the sample size gets a little bit bigger, it's moderate size, say 10 to 20 samples, we see that the red curve and the blue curve look similar, but of course the blue curve has a higher peak because the tails aren't as fat. To investigate this, we take a small sample, we take 6 samples from the normal random variable, and in this case we're choosing parameter values for mu and sigma of 6 and 4. We do that repeatedly, and what we notice, of course, is that the mean of the estimator is equal to the mean of the random variable, and of course there's some variance, which is also shrinking in proportion to root n. And of course, we standardize the mean in 2 ways, using sigma from the random variable and using our estimate for sigma, which we got from the data set itself from those 6 samples. And we see that by and large, the curves don't look very different, although when we superimpose them on each other, we do see indeed that the curve that we're generating when we have to use the estimated value of sigma has fatter tails and a smaller peak, so it will not probably suffice to use the normal as an approximation for a sample size this small. But now we go one step further and say, okay, well, how does the estimate for the variance stack up to the true variance of the random variable? So we do that, and again, we want to make this independent of the sample mean, the sample variance, so we standardize our estimate for the variance. First thing we notice that's a little interesting is that the random variable that describes the distance between sigma squared and our estimate for sigma squared using the sample mean is not symmetrical. Of course, one reason to see why is because sigma squared is always positive, and of course our value is always positive because they're sums of squares. We're seeing here is the chi-squared distribution for n minus 1 degrees of freedom, so in this case 5 degrees of freedom, looks almost exactly like our empirical distribution. And what we can see is the amount of extra variance that we're adding, of course, is described by the chi-squared distribution. So what that means is we can fix our attempt at using the standard normal by taking a standard normal and dividing by a chi-squared random variable. Of course, not quite. In this case, we're going to actually divide by the chi random variable, which is just the square root of the chi-squared, and that's just because the chi-squared gives us our error in variance space, but we would rather have it in standard deviation space because that's the space that the distribution lives on. So that's really nice. So what that tells us is, oh, we want to describe the red curve. Well, here it is. The red curve is described by a standard normal divided by the square root of the chi-squared distribution. So we take the random variable that we are trying to substitute for the standard normal and failing, and we realize that we're off by the extra variance we have. It's just the chi-squared random variable. So we just divide, and the new random variable, it's the random variable that describes the distance from the true mean in a sample of data after we've standardized and normalized by the sample variance. Let's just take a pause and let's talk about the 2 new random variables that we just introduced, and we just kind of blew by both of them. So first off, the chi-squared distribution. Like the t-distribution, the chi-squared distribution is also a sampling distribution, so it doesn't make sense really to use it for the to model phenomena in the natural world. However, it can be used really well to model disparity between counts or observations in the natural world. So, and that's because the chi-squared distribution is the distribution that represents sums of squared normals, and differences in variance are differences in sums of squares. So analysis of variance tests for contingency tables, goodness of fit test to compare 2 distributions, the chi-squared distribution will pop up all the time there, and it's one of the most widely used random variables in statistics. Of course, the t-distribution really needs no introduction. So of course we can define the t-distribution, just how we built it, right? We can say that the t-distribution represents the distance of the true mean from the sample mean after, of course, we've standardized our random variable. It allows us to make inferences where we can assume normality of the underlying random variable, but we don't have enough samples to accurately estimate our parameters. In particular, we don't have enough samples to accurately estimate the variance. To provide final justification for why the t-distributed random variable is useful, we can look back at our example where we have 10,000 tests, and of course that when we use the t-distribution rather than the z-distribution with an estimated parameter, we get the correct amount of false positives, or the desired or the expected amount. Of course, the t-distributed random variable does not work when the sample size is very, very small. So for example, when you only have 2 samples, the t-distribution converges to something that's called the Cauchy distributed random variable. So the t-distribution with 2 samples, or 1 degree of freedom, is equivalent to the Cauchy distribution. We talked about such a distribution when we investigated the St. Petersburg paradox in the discrete space, and this distribution is often used as an example for a very, very badly behaved distribution, because since the mean is infinite as well as the variance, of course you cannot expect sums of this distribution to converge to the normal. And interestingly enough, this distribution is simply the ratio of 2 standard normal random variables. We do have another sampling random variable. The F distribution is the ratio of 2 chi-squared random variables. You can sort of see where that's going. If you imagine 2 models, and each model is trying to describe a relative amount of variance, the ratio between them can be used to determine which model is better. So the F distribution is used for model evaluation or model comparisons, and it's just a ratio between 2 chi-squared random variables divided by their degrees of freedom. Quick recap, right? We talked about very briefly the continuous uniform random variable and the continuous exponential random variable, which is of course the continuous analog of the geometric random variable. Then we got right into the recap of the law of large numbers and the central limit theorem. And we can distinguish the two, remember, by saying that there is a journey and a destination. The destination is the law of large numbers, but the journey is the central limit theorem. So that's going to be helpful to understand that. And then of course we talked about the sampling distributions, and we talked about how we can derive them and how they're related. And the important ones that we don't want to forget are the chi-squared random variable, the t-distributed random variable, and the f-distributed random variable. And of course, as always, we never want to forget the normal distributed random variable. So we now have our chart, right, our world of random variables, and we can look around and we can see them up and down, right? We have discrete and continuous, and the only random variable that we may have not spoke about is the beta distributed random variable. If we did mention it in the discrete part of the course, but we talked about it in context of the beta binomial random variable, and we talked about how important that random variable is. And of course, just the beta by itself is also very important. It can be used to approximate many other random variables. And one really useful thing that we haven't talked about is it can be used to model the order statistics of the uniform random variable. That said, I think we have a good set of random variables. It's been worth it to walk through this path to understand these random variables, and just so we don't feel too overwhelmed, or we don't feel like we learned too many random variables, I've compiled a list of other named random variables that have a use. Now, obviously, you don't have to know these ones that are going to pop up, but you can learn them all if you'd like. But to give us a taste, here's 160 popular random variables that all are worthy of a name. And these random variables will escort us out of the lecture, and I will see you guys next time.